A single ton of sand is priced at just $30. When it is heated to 400 degrees, it retains enough thermal energy to keep a residence warm for 3 full days. This material never degrades, and it never freezes. Back in 2022, engineers in Finland successfully heated an entire municipality through a harsh Arctic winter by utilizing sand stored within a steel silo. Ancient Persians had already mastered these principles of physics thousands of years ago. By the conclusion of this video, you will find out precisely why this technology was buried in America and exactly how you can construct one yourself. The ground beneath every house remains at a steady temperature, yet sand possesses a capability that soil alone simply cannot match. Sand can be supercharged and heated to levels that would boil water 3 times over without requiring any pressure vessels, without utilizing exotic chemistry, and without any danger of freezing or breaking down. The physics driving this process is so straightforward, it almost feels like a shortcut. Sand has a specific heat capacity of about 0.8 kilojoules per kilogram per degree Celsius, while water holds roughly 5 times more heat per kilogram and seems to win on paper. The numbers shift completely in practice. Water reaches its boiling point at 100 degrees Celsius. To push it any higher, you need industrial equipment, pressure vessels, and safety systems that cost thousands of dollars. Conversely, sand can be heated to 600 or even 1,000 degrees Celsius, and it simply remains stable. There is no phase change, no buildup of pressure, and no inherent danger from the storage medium. This temperature range is where sand completely outperforms water. Here is the specific figure that changes the entire equation. 1 cubic meter of dry silica sand, when heated from 20 to 200 degrees, stores approximately 67 kilowatt-hours of thermal energy. That equates to roughly 3 days of heating for a small, well-insulated home. The sand itself costs between $30 and $80 per ton, depending on your location. Compare that to lithium battery storage, which costs between $300 and $600 per kilowatt-hour. The gap in cost is truly staggering. We are discussing pennies per kilowatt-hour of thermal capacity compared to hundreds of dollars. Furthermore, sand never wears out. A properly constructed sand storage system has a theoretical lifespan exceeding 50 years. Sand is chemically inert, meaning there is no fire risk from the medium itself, no toxic off-gassing, and no hazardous waste at the end of its life. There are no rare earth elements required from the Congo and no fragile supply chains reaching back to refineries in China. It is just sand being heated up and giving that heat back. You could pass this system down to your grandchildren, and they could pass it to theirs. The same sand will perform the same function a century from now. Engineers refer to this as sensible heat storage. It represents the simplest and most economical method of storing thermal energy ever created. You put heat in, and you take heat out. There are no phase changes, no chemical reactions, and no moving parts within the medium. Research published in 2025 confirms that sand thermal energy storage offers high capacity and long-duration storage at extreme temperatures. It is perfectly suited for large volume applications and remains cost-competitive with fossil fuel heat sources when combined with renewable electricity. The physics is elementary, so elementary, in fact, that ancient civilizations figured it out thousands of years before the word thermodynamics even existed. 2,000 years ago in Rome, engineers constructed structures that heated entire cities from underground. This system was known as the hypocaust. Hot air from a wood-burning furnace flowed beneath raised stone floors and through hollow clay walls, warming every surface in the building. The baths of Caracalla in Rome utilized this technology, as did the Great Bath Complex at Bath in England, and the ancient city of Timgad in Algeria. As early as the 1st and 2nd centuries, engineers were creating some of the first climate-controlled buildings in history. However, the Romans were not simply burning fuel around the clock. The true genius lay in the thermal mass. Stone, brick, sand, and clay, packed beneath those floors, absorbed massive amounts of heat while the fire burned. When the flames eventually died down, the mass continued radiating warmth for hours. The building itself became the battery. In medieval Northern Europe, this principle was refined into something even more remarkable. The heat storage hypocaust was an underground furnace, topped with piles of granite stones that could be heated to extreme temperatures with a single firing. Those stones then released hot air through vents in the floor, not just for hours, but for days. One fire could provide warmth lasting 48 hours or more. Imagine a monastery in 14th century Livonia, with snow piled against the walls and wind howling across frozen fields. Inside, the monks walk across warm stone floors, heated by a fire that burned out yesterday morning. Historian Klaus Bingenheimer estimated in his landmark 1998 study that medieval Europe contained at least 500 hypocausts, 154 of which were specifically designed for heat storage. Since then, researchers have uncovered many more. These systems were born from combining the ancient Roman method with stone heat traditions practiced by indigenous peoples of present-day Finland, Estonia, and Latvia, who had been heating saunas this way for centuries. Across the Pacific, the Korean Ondol system achieved the same result through the same physics. Underfloor channels carried heat from cooking fires through stone and clay thermal mass beneath the living space. Historical records in the Samguk Sagi describe these systems maintaining interior temperatures between 64 and 72 degrees Fahrenheit through brutal Korean winters and summers alike. Ondol heating remained the standard in South Korean homes until the 1960s. In the deserts of ancient Persia, engineers devised yet another variation. Thick mud brick walls and dense clay floors absorbed the scorching daytime heat and radiated it back through cold desert nights, when temperatures could plunge by 40 degrees in a matter of hours. The same thermal mass that kept interiors cool during the day became a gentle heater after sunset. Entire villages in present-day Iran and Afghanistan still bear the architectural fingerprints of this approach. Walls a meter thick, floors of packed earth and sand, and buildings that breathe with the cycle of the sun. Romans, medieval Europeans, Koreans, Persians, and indigenous Scandinavians, every civilization that faced extreme temperatures independently converged on the same answer: store heat in mass, release it slowly, and let physics do the work. Across 5 continents and 3,000 years, the same solution appeared repeatedly because the laws of thermodynamics demanded it. Then, in a single century, the solution vanished from construction entirely. In 2016, a young Finnish engineering student named Tommi Aronen was researching water-based energy storage systems for his master's degree. While reading an article about traditional Finnish fireplaces made from stone and sand that were designed to hold heat for days after a single firing, he had what he would later describe as a light bulb moment. Not water, not chemicals, not lithium, sand. 6 years later, the BBC broke the story that would bring this idea to the world. In the small town of Kankaanpää, Finland, a steel silo stood 7 meters tall and 4 meters wide. Inside sat 100 tons of locally sourced sand. It was the world's first commercial sand battery. Built by Aronen's company, Polar Night Energy, this system delivered 200 kilowatts of thermal power with 8 megawatt-hours of storage capacity. It connected directly to the town's district heating network, warming homes, commercial buildings, and even the local swimming pool through the Finnish winter. Outside, temperatures plunged well below freezing, but inside, the buildings stayed warm, powered by sand. The engineering is remarkably simple. Electricity from the grid or from local renewable sources powers a resistance heater inside the insulated steel container. A fan circulates hot air around the sand, heating it to as high as 600 degrees Celsius. Thick insulation surrounding the container keeps the sand at those temperatures for hours to months, depending on the system size. When heat is needed, a heat exchanger transfers warmth from the sand into the district heating water loop. According to Polar Night Energy, the system achieves heat recovery of up to 99%. But Kankanpää was only the beginning. In 2024, Polar Night Energy commissioned a far larger system in the town of Pori, Finland. Picture a steel cylinder 13 meters tall and 15 meters wide, filled with 2,000 tons of crushed soapstone. This sand battery delivers 1 megawatt of thermal power with 100 megawatt-hours of storage, 10 times the size of the original. Engineers reported it would slash Pori's carbon emissions by 70%. In summer, when renewable energy floods the Finnish grid, this single battery stores almost a month of the town's heat demand. In winter, it covers close to a full week. Eronen explained that cities like Tampere already have district heating systems circulating hot water across entire neighborhoods. His sand batteries plug directly into that existing infrastructure, allowing communities to switch to renewable heat quickly and affordably. The technology earned Polar Night Energy a place on Time magazine's list of best inventions of 2025, and they are not slowing down. A 250 megawatt-hour sand battery is scheduled to begin construction in the city of Lahti, Finland, in early 2026. This project, backed by a grant from the Finnish government agency Business Finland, will attempt something even more ambitious: converting stored thermal energy back into electricity. The expected electrical efficiency is approximately 30 to 35%. When used for combined heat and power production, overall efficiency could reach 90%. Sand generating electricity in 2026. Thousands of tons of sand heating. Thousands of homes. Documented, measured, and verified by independent researchers across multiple Finnish winters. The technology works. It has been proven at laboratory scale, household scale, and municipal scale. So the obvious question is this: why does none of it exist in America? Open the International Residential Code and search for any provision allowing sand-based thermal storage integrated into home heating systems. You will find nothing. The code was written around mechanical equipment: furnaces, heat pumps, air handlers, and ductwork routed through crawl spaces and attics. Every compliance pathway assumes a manufactured appliance sitting in a utility closet consuming electricity or gas on demand. A steel container full of heated sand does not fit the template, and what does not fit the template cannot be approved. Picture a contractor walking into a county building department carrying blueprints that show a sand battery in a client's garage. The inspector opens the codebook and flips through looking for the relevant section. There is nothing there. No performance pathway for solid media thermal storage, no testing standard, no approval mechanism. The inspector shakes his head and stamps the plans rejected, not because the technology failed a test, but because the paperwork to test it does not exist. ASHRAE publishes Standard 90.1, which sets minimum energy efficiency requirements for buildings across the United States. These calculations assume mechanical heating and cooling as the baseline for all thermal comfort. A sand battery that heats a home using stored renewable energy cannot generate a compliance score because the formula was never designed to measure it. The technology is invisible to the regulatory framework. It is not banned. It is simply unrecognized. In practice, that amounts to the same thing. The International Energy Conservation Code provides zero compliance credit for passive or solid media thermal storage. Builders receive no incentive whatsoever to install systems that eliminate the need for conventional equipment. The entire code structure rewards buying machines and penalizes simplicity. Now, follow the money and the picture sharpens. The American residential HVAC market generates tens of billions of dollars every year in equipment sales, installation contracts, maintenance agreements, and refrigerant charges. Currently, more than 45% of electricity consumption in American buildings goes towards thermal uses like space heating and cooling. That is an enormous river of revenue flowing to manufacturers, distributors, contractors, and utility companies every single month. Every sand battery installed in an American home is a furnace that never gets sold, a compressor that never gets replaced, a service contract that never gets signed, and a refrigerant charge that never gets topped off. Walk through any suburban neighborhood in Houston or Chicago or Phoenix and count the HVAC units humming on rooftops and concrete pads beside every house. Each one represents a recurring revenue stream that a pile of heated sand would permanently eliminate. Imagine executives in boardrooms studying market projections on glowing screens. Imagine lobbyists in government hallways carrying briefcases full of position papers. Imagine trade group representatives sitting on the very code committees that decide which heating technologies American families are permitted to install. The system is not suppressing innovation through some grand conspiracy. It is protecting existing revenue through inertia. Codes written by industry insiders naturally favor industry products. Technologies that eliminate the need for those products never appear in the code book, not because they were rejected, but because they were never proposed. Finland succeeded in part because its infrastructure was ready. District heating networks already circulate hot water through entire neighborhoods, creating a natural distribution system for centralized thermal storage. America's heating model is fragmented by design. Every home is an isolated thermal island with its own furnace, its own thermostat, and its own monthly utility bill. There is no shared infrastructure to plug a community sand battery into. The system was built to sell individual machines to individual homeowners, not to share solutions at scale. The codes will not recognize it, the industry will not sell it, and the infrastructure does not support it. But none of that changes the physics. And the physics says you can build one yourself. A basic sand battery built from a 200-liter steel drum filled with dry silica sand and fitted with standard resistive heating elements costs between $180 and $320 in total materials. That includes the drum, the sand, the elements, mineral wool insulation, a temperature controller, and a small inline fan. A larger custom-built system providing 50 or more kilowatt-hours of storage runs between $500 and $2,500 depending on insulation quality and heat exchanger design. The sand alone costs under $10 for a 200-liter drum. The charging system could not be simpler. Solar photovoltaic panels wired directly to resistive heating elements. No inverter is required for direct current resistance heating, no battery management electronics, and no sophisticated controllers. Just sunlight converted to electricity, converted to heat stored in sand. Off-peak grid electricity at overnight rates works as an alternative or supplementary charging source for cloudy stretches. A 2 to 4 kilowatt solar array can provide enough energy to heat a 200-liter drum of sand toward its target temperature of 150 degrees Celsius over a few sunny days. Getting that stored heat out of the sand and into your living space requires a heat exchanger. The simpler approach uses air. A low-wattage fan pushes room air through metal pipes embedded in the hot sand. The air absorbs heat from the pipes and flows into the room through ducting or directly through a wall vent. At small household scales, this delivers 500 watts to 2 kilowatts of continuous heat output, enough for steady background warmth in a well-insulated space or for preheating domestic hot water before it reaches your conventional water heater. For anyone building their first system, keeping the operating temperature below 150 degrees Celsius is the critical safety threshold. Below that number, you can use standard electrical wiring, standard insulation materials, and standard plumbing fittings. If you push above 200 degrees Celsius, you enter the territory of high-temperature rated wiring, refractory materials, and specialized components that significantly increase both cost and complexity. The sand must be completely dry. This is absolutely non-negotiable. Moisture trapped in sand at high temperatures turns to steam. Steam creates pressure, and pressure in an enclosed vessel is dangerous. Dry silica sand eliminates this risk entirely. Before loading sand into your drum, spread it on a metal sheet in direct sun for 2 full days. Alternatively, bake it in batches in a standard oven at 200 degrees Celsius for 1 hour per batch. Test the sand by heating a small sealed sample and checking for any condensation on the interior walls of the container. Temperature monitoring with automatic shutoff is essential. A basic thermocouple connected to a relay controller that cuts power at your target temperature costs under $50. Place the storage unit in a detached workshop, a garage, or a buried outdoor installation. Do not place it inside the primary living space when it is operating at high temperatures. Common sense and basic electrical safety apply just as they would with any heating appliance. Insulation is what separates a working system from an expensive disappointment. A poorly insulated drum loses its stored energy in hours. Mineral wool wrapping with an outer layer of rigid foam board creates a cost-effective thermal barrier. Plan for at least 150 millimeters of insulation on all sides, including the top and the bottom. Every millimeter of insulation you add extends the hours as sand holds its heat. The beauty of this approach is its modularity. Start with a single drum as a proof of concept. Measure the charge time, the discharge rate, and the overnight heat loss. Learn the behavior of your specific setup. Then add a second drum, and then a third. Multiple drums connect in parallel, feeding warm air into a shared distribution duct. You can scale from heating a workshop to supplementing your entire home, 1 drum at a time. A single 200-liter drum of sand at 150 degrees Celsius stores approximately 7 to 8 kilowatt-hours of thermal energy. That covers a full day of supplemental heating in a well-insulated home. 4 drums give you 3 to 4 days of thermal buffer. That is enough to ride through a cold snap on nothing but stored solar energy. For those with existing hydronic heating, such as radiators or underfloor water loops, a simple air-to-water heat exchanger allows the sand battery to feed directly into what you already have. Hot air from the sand heats one side of the exchanger. Circulating water picks up that warmth on the other side and carries it to your radiators. No modification is needed to the existing distribution system. Maintained properly, this setup lasts decades. The sand does not degrade. It does not lose capacity. It is the same sand in 50 years as it is on the day you pour it in. Sand-based thermal energy storage achieves efficiencies near 90% at scale. When paired with low-cost renewable electricity, it reaches a levelized cost of heat competitive with natural gas and propane. Those are not projections from a startup pitch deck. Those are findings published in peer-reviewed engineering journals in 2025. The physics does not require government subsidies. It does not require technological breakthroughs. It requires only that someone builds the container, fills it with sand, and points a heat source at it. In Cancayanpea, a steel silo full of sand heats a town through Arctic darkness. In Porvoo, 2,000 tons of crushed stone slash emissions by 70%, while families sleep warm. In Lethe, engineers prepare to prove that heated sand can generate electricity and feed it back to the grid. Across garages and workshops in Europe and America, builders with welding equipment and bags of silica sand are proving every weekend that the concept works at any scale. The Romans knew it when they stacked stones beneath marble floors and let thermal mass carry warmth through Mediterranean nights. Medieval monks knew it when they fired granite hippocausts once and heated stone halls for days on end. Korean families knew it for 3,000 years before Western architects forgot it existed. The knowledge survived every empire and every dark age because physics does not care about marketing budgets, regulatory capture, or the quarterly earnings reports of furnace manufacturers. Sand is the most abundant mineral on Earth's surface. It has been absorbing heat from the sun and releasing it through the night for 4.5 billion years. It was storing thermal energy before life existed on this planet. It stored heat beneath Roman bathhouses and Korean farmhouses and Finnish saunas. It is storing heat right now in steel silos across Finland, where entire towns stay warm through the darkest months of winter, powered by nothing but last summer's sunlight. The codes will catch up. They always do eventually. But you do not have to wait for permission to understand the physics. You do not need a manufacturer's blessing to fill a drum with sand and wire a solar panel to a heating element. The knowledge is yours now. The materials are at your local hardware store. The sun is overhead. The sand has been waiting. It has always been waiting. If this story has changed the way you look at the very ground beneath your feet, please subscribe to the channel and like this video. We are uncovering the history and technology that they have tried to keep hidden. Let's build a more resilient future together. The next treasure of forgotten knowledge will be revealed very soon.